Yes, great. Okay, so Sander Schouws will tell us all about the Rebels program and first results from like ALMA. Yeah, take it away, Sanders.
Thank you. Good afternoon. My name is Sander Schouws. I'm a PhD candidate at the Leiden Observatory. And today I'll show some results from the Rebels survey. So Rebels is a 70-hour large program on the ALMA telescope, targeting a large sample of luminous galaxies in the epoch of Reionization. So why would you want to use ALMA for studying these high redshift galaxies? Why is ALMA an ideal instrument for this? Well, let's take a step back and look at some questions that we have about high redshift galaxies. For example, how quickly do they build up dust? How important is dust obscuration in these galaxies? How much star formation rate is hidden by dust? And we need to take account for that in our star formation rate census. And as you can see, the number of data points at high redshift is quite limited. Another thing is, how do we get spectroscopic redshifts? For most galaxies, we don't have spectroscopic redshifts, and that's because the universe is increasingly neutral and absorbs the Lyman alpha line, and basically taking that out of the picture. So we need to find another line that can take over that job. And finally, we would like to know the precise physical conditions where the star formation rate is taking place in these galaxies and how it's different from the low redshift universe. And it would, of course, be very interesting to know. A nice thing is, with ALMA, we can shed light on all of these points. So, for example, we detect the dust continuum directly. So we can directly measure the obscured star formation in these galaxies and their dust masses. And we have some very luminous emission lines. Specifically, the C+158 microline and the O388 microline are sufficiently luminous that you can blindly scan for them and get redshifts that way. And finally, there are a lot of emission lines in this part of the spectrum. And just like optical lines, you can use the line ratios of these lines to get constraints on the physical properties of these galaxies. So ALMA is really able to answer all of our questions if we want to use it like that. So this is nice in theory, but does it work in practice? And what we've shown in our pilot studies using this C+ line specifically is that you can blindly scan for this line and efficiently detect the spectroscopic redshift for a large sample of galaxies. And on the other side of the world, some Japanese groups have used the O3 emission line to also detect spectroscopic lines of very exciting targets at very high redshifts. So it's definitely possible to do this, and we want to do this for a much larger sample, and that's where Rebels comes in. So I've selected a sample of 40 sources between redshift 6.5 and 9.5. And we've searched a huge area on the sky, so 7 square degrees. And that means that we're scanning such a large area that's not really feasible to do with James Webb. So this sample is something unique, even after James Webb is launched, because our galaxies are so bright and so rare on the sky. And to be confident in our photometric redshift estimates, we use 3 independent people to do this. And then we design a so previously I showed that our pilot studies have mostly used the C+ line, and the Japanese groups have with great success mostly used the O3 emission line. So that begs the question, which emission line is better to use if you want to find the redshift of a source? And that actually depends on 2 things. So it depends on the line ratio you expect, and it depends on the atmosphere. So you can do a calculation and look at the line ratio from previous detections. So what we find is that O3 is in generally more luminous than C+. But because the atmosphere for C+ is a little bit better, it's actually more efficient to use C+ at lower redshifts. And that holds true up to about a redshift 8.5. And then it's actually more efficient for the typical source to use O3. So that's the strategy we apply to our sources as well. So what we do is we do a spectral scan. And in practice, that means that you use ALMA to do different tunings, because the redshift coverage by ALMA and instantaneous tuning is quite limited. So you spend a lot of observing time actually looking at parts of the spectrum where there's no emission line. And you might think, well, that's a waste of time. But actually, that's not really the case, because C+ is much easier to detect than the dust continuum. So that means if you want to detect the dust continuum, you need to integrate long time anyway. So a spectral scan is not really a waste of time. Actually, this is a very efficient method to both get a spectroscopic redshift, you get the emission line to probe the physical properties, and you get the dust continuum in one go. So does this actually work? Well, I'm glad to tell you that it works really well. What I'm showing here is a large, well, basically all our detections, and you can see that there are most of them have very high signal to noise. So what I show is the the rest frame UV emission in the background. With the blue contours, we show the C+ emission, and with the orange contours, we show the continuum emission. And you see that for most sources, we both detect the dust continuum and the C+ quite at high significance. And you also see that there are some interesting things going on. For some sources, there are some misalignments, and for other sources, everything is very well aligned. So this is definitely something we're looking at in more detail. So let's take quickly a look at some of the statistics of our detection. So does the spectroscopic redshifts we find agree well with the photometric redshifts? Well, luckily they do, as you can see in that figure. There might be a slight bias at high redshifts, but that's not really, well, we're looking into that in more detail. So looking at the fraction of sources we detect as a function of UV star formation rate, you can see that for high star formation rates, we detect most sources. And this becomes even more apparent when you include the obscured star formation rate. So if we look at the total star formation rates, not only the UV, then for our sensitivity limit, we basically detect, well, by far the largest, the majority of sources, despite the fact that we're only using spectroscopic photometric redshifts. So our survey is working really well. And we've created a very interesting and quite large sample of interesting sources. So what can we do with that? Well, one thing we can look at is, for example, the kinematics of these sources. And what we see is that for a significant fraction of our sample, we find quite clear velocity gradients. Now, this enables us to look, for example, at the effect of rotation versus dispersion support in these galaxies, and maybe even at mergers. But you should keep in mind that this is very low resolution data, and that's actually the limiting factor of our data at the moment. So we've created a model that fits the data cube in three dimensions for a rotating disk model, a thin rotating disk, and a merger model. And what we find is the residuals for both these models are quite similar. So it's not really possible at the current resolution to tell both scenarios apart. But nevertheless, we'll be able to provide at least some insight into the fraction of sources that's dispersion versus maybe rotation or merger, and also their dynamical masses. Something interesting that we observed and completely didn't expect is that next to our target sources here in the middle of our field, we find that there are additional sources, so at the same redshift, that are nevertheless completely obscured in the rest frame UV. So that's something quite strange. These sources are not extreme. Their star formation rates are not extremely high like ULURCs or or SMGs, but nevertheless, they're completely invisible in the rest frame UV. And we even have HST observations for one source and still invisible in even those deep observations. So that means that with the current observation, the current surveys that look at that try to make a census of the star formation at high redshifts, we might be missing a significant fraction of the sources. And this is discussed in more detail in Yoshi's Fudamoto's paper that's upcoming. Okay, finally, I want to show some results from the pilot. We're still working on the Rebels analysis for this, but we're not really limited by the number of data points. So what I show here is the IRX beta relation that we often use to correct UV-based star formation rates to include obscured emission. So it's really important that we understand this well to take proper sense of the total amount of star formation going on at high redshifts. So we would like to quantify that, and one way of doing that is fitting it. But one big assumption comes in here, and that's the assumed dust temperature of your SED model. And what I show here is that the assumed dust temperature has a huge effect on the fit you get. It's more quantified here. So this is the slope of the dust attenuation curve. So that's what we use to correct the observations. And if you use a dust temperature of 40 Kelvin, and well, it's also dependent on the intrinsic beta slope. So if you assume intrinsic beta slope and you also assume a dust temperature of 40 Kelvin, it's mostly consistent with SMC. But then if you move to higher dust temperatures, it becomes consistent with Calzetti. So there's a huge difference between this. And the same goes for the dust masses. If you want to understand how the dust mass is formed, for example, through supernovas or maybe grain growth in the ISM, then we need to understand the total dust mass, and that's not really possible without understanding the dust SED. So our current understandings really hold back by our lack of understanding of the dust SED, and we need more observations to to solve this issue. Okay, so finally, I want to conclude my presentation by showing showing some things we're working on and some papers we're working on. So we're of course looking at the dust law and the evolution of dust. We're looking at kinematics. We're looking at the far infrared and C+ luminosity functions. We're also looking at C+ halos and outflows and much more things. We're of course also working on a public data release. You can see the concept website here. Hopefully that's coming soon. And I would like to emphasize that our sample is an ideal list of targets for follow-up observations. So I already showed that we really need higher resolution observations to understand the kinematics of these galaxies. And we've done that for one source in our pilot, and you can see the amazing improvement we get. And of course, to understand the variety in galaxies at these redshifts, we need a larger sample to be able to understand this. Also, the O3 line is an ideal target to follow up. So if you target C+ and O3 and the dust continuum for both of them, you get a much better insight in the conditions of star formation. And that's probably, well, Joris is going to talk about this in the next talk, so that's going to be really interesting. And also, the nice thing with targeting O3 is that for you basically get the dust continuum for free. So there's the dust continuum point at about 90 microns, so that's closer to the peak of the dusticity, so you get a better idea of what the dust temperature is. And besides that, there are, of course, other emission lines that you can target, like nitrogen and oxygen. We have also approved very deep observations on the CO line for one of our galaxies. So we'll be able to constrain the gas content in that galaxy, hopefully really well. And yeah, that's on the JWST telescope. As Mauro previously showed, for a large fraction of our sources, we will also be receiving IRView observations at R of 100. So we'll be able to probe the UV and optical spectrum from Lyman alpha to H alpha and connect that to the ALMA observations. It's going to be very interesting to see what comes out of this. And finally, we have also a lot of incoming ground-based data on Lyman alpha line and metal lines in the rest frame UV to maybe also constrain something like the AGN contribution in these galaxies. So I hope I was able to transfer some of my enthusiasm about this very exciting survey in this presentation. I would like to thank you for your attention, and questions are very welcome.
Great. Thank you, Sander. So we'll probably have time for one quick question if y'all want to type it in, and then we'll move on after that.
Yeah, there's a quick question here. What is the effect on your conclusions because you're using a UV selection of your targets?
Yeah, of course. That's a limitation in our sample selection. Of course, it's the best we can do at the moment, right? So, but I agree, it's a limitation, and we're working with simulators, and we're looking at ways of properly estimating the completeness of our sample and doing things like that. Yeah.
Yeah, it's really beautiful data, and it's just exciting to see. Obviously, it's a good starting sample. So cool. All right. Well, we're out of time for Sander's talk, but please feel free to pepper him with questions in Slack some more.